Alrighty, let's get to the other half of the midterm review here. So the next problem, what it wants us to do is it wants us to solve the following system using an LU factorization of a matrix, right? And so what does that mean? Remember, if you have a matrix A, I don't know how this got to be green. If you have a matrix A, you can express it as the product of a lower and upper triangular matrix, right? Where here this is going to be something like 1, 1, 1, X, Y, Z. So I'm writing this in the case of a 3 by 3, right? So it's like 1, 1, 1, X, Y, Z, and then like A, B, C, 0, D, E, 0, 0, F, right? This is in the 3 by 3 case. This is an LU factorization of a matrix. It's where you express a matrix as a product of a lower triangular and an upper triangular matrix, right? And by lower triangular, that means all of the entries are in the lower triangle of your matrix. And for an upper triangular, all your entries, all your non-zero entries are in the upper triangle of your matrix here. For a lower triangular matrix, we require that we have ones along the diagonal here, right? And so we're going to see, or we're going to remind ourselves, how do we solve a system via an LU decomposition of a matrix? So here's number 3 from this practice exam. Let's say we want to solve the system x1 plus 2x2 equals 1, 2x1 plus x2 plus 3x3 equals 2. And then x1 plus 2x2 plus 3x3 equals 2, right? Now, how are we going to do this, right? Well, let's first write the corresponding system or the corresponding matrix form of the system. That would be 1, 2, 0, 2, 1, 3, 1, 2, 3. That's your coefficient matrix, right? You just look at all the coefficients. And then the first column of the matrix is all the x1 coefficients. So 1, 2, 1. And then for x2, it's 2, 1, 2. And then for x3, it's 0, 3, 3, right? Times the solution vector here, x1, x2, x3, and then this equals 1, 2, 2, right? This is how we would represent the system as a product of matrices. Now, let's say we have to solve this using, because how this instructor set the problem up is that you have to solve this, or he asks you, or they ask you to solve this by first finding the LU factorization of the matrix A, of the coefficient matrix. So let's find the LU factorization of the coefficient matrix here. So we want 1, 2, 1, 2, 1, 2, 0, 3, 3. This needs to be equal to a lower triangular matrix times an upper triangular matrix, and we'll say A, B, C, 0, D, E, 0, 0, F. And we are tasked with solving for all of these unknowns, right? To find the LU decomposition or the LU factorization here, we have to know what X, Y, and Z are. We have to know what A, B, and C, D, E, and F. We have to know what all of these are, right? Well, to do this, let's multiply this out on the left, right? We have the product of two matrices on the, or excuse me, on the right, we know how to multiply two matrices. Well, how do we multiply two matrices? We take the first column, and then we take the dot product of that column with the first row vector, right? And so that would be A, and then we take the dot product of the second column with the first row vector, and that's going to be B, and then we take the dot product of the third column, CEF, with the, we take the dot product of that column with the first row. So that's CEF, dot product 1, 0, 0, that's C. And then we go to the next the next row, right? Now we go A0, 0, dot with X1, 0, and that looks like it's going to give us AX. Then we'll go to the second row. So we have the BD0 column dot with X1, 0. That's going to be BX plus D. And then for the third one, that's going to be CX plus E, right? I'm just doing the matrix multiplication here so that we can equate these two matrices and hopefully solve for all of these unknowns. Cool. So what's the third row? Well, we're going to take A0, 0, dot product with YZ1. That looks like it's going to give me AY, and then we're going to have BY plus DZ. And then for the last one, we're going to have CY plus EZ plus F. Okay, and now what do we know? We know that these two matrices have to be equal. And if these matrices are equal, that means every entry is equal. So the A11 entry of the right-hand side has to be equal to the A11 entry on the left side. So we get A equals 1, B equals 2, and C equals 0. Right? Well, if A equals 1, and that's all from just setting equality component-wise. Now let's go to the A21 position here. This one. Well, we know A is 1, so that's really just X. But we know that X has to be equal to 2 then. Right? Because AX has to be equal to 2. And then we have BX plus D has to be equal to 1 because we set the A22 entries equal to each other. And we know B and D are, or excuse me, B and X are 2. And so this looks like that would imply D is -3. And then we have CX plus E equals 3. But then C is 0. So that means E equals 3. And we keep going, right? We know A equals 1. So A times Y equals 1 implies that Y equals 1. And then we have B and Y are 2. So we have, well, let's see here. We have BY plus DZ. That has to be equal to 2, right? And so then we would have BY, which is going to be 2 times 1. So 2 plus, or let's say minus 3Z, because D is -3, minus 3Z equals 2. You subtract the 2 from both sides, that tells us that Z is going to be 0. And then lastly, we have that CY plus EZ plus F is equal to 3, but CY is 0 because C is 0, EZ is 0 because Z is 0, which means that F is equal to 3. And now, we found every variable here, or every unknown, and I'll box them here. We found A, B, C, D, E, and F, and then we also found X, Y, and Z, just by taking this product and then trying to figure out, going through this kind of logic of, okay, well, if the entries have to be equal on the left and right-hand side of the equation, then you set up all these equalities and you can find these unknowns relatively quickly. So putting all of this together, we get that 1, 2, 1, 2, 1, 2, 0, 3, 3. The LU decomposition of this matrix is then we get 1, 2, 1, 0, 1, 0, 0, 0, 1 times 1, 2, 0, 0, -3, 3, 0, 0, 3. Right? And this was because X equals 2, Y equals 1, Z equals 0. Right? We found that out on the previous page. X equals 2, Y equals 1, wherever it went, and Z equals 0. And then we had the A was 1, B was 2, C was 0, et cetera, et cetera, et cetera, right? And so we just went back to the top step there and filled in what all these unknowns were. Cool. Now, how do we use this to solve the system? Well, what we do first is we set up, let's set up first Ly equals B, and we want to solve this first, right? If we solve this first, then we could solve ux equals y. This would be our solution x, right? So let's first set up and solve Ly equals B here. And so our matrix L is the lower triangular matrix. So this is L, and we're going to set up L. So 1, 2, 1, 0, 1, 0, 0, 0, 1 times y, right? These are new unknowns that we're solving for. And this is equal to B, which was 1, 2, 2, right? Just from the original system, right? That was B from the original system. Okay. Well, then, what does this mean? We get this following system. We get y1 equals 1, 2y1 plus y2 equals 2, and then y1 plus y3 equals 2. Well, if y1 equals 1, then that implies that y3 equals 1, and then that implies that y2 equals 0, right? And so we have y1, y2, y3, and so really, then we have that y is 1, 0, 1, and what we want to set up now is ux equals y, right? Because now we're using the upper triangular part of this to solve the system. And so the upper triangular matrix was 1, 2, 0, 0, -3, 3, 0, 0, 3, and then we have x1, x2, x3, and then this equals y, which is 1, 0, 1. And what system do we get here? We get the following system: x1 plus 2x2 equals 1. We get -3x2 plus 3x3 equals 0. And then we get 3x3 equals 1, which implies that x3 equals 1/3. But if x3 equals 1/3, you can see from the second equation here that x2 equals x3, which implies that x2 is 1/3. But then if you plug in x2 equals 1/3 to the first equation here, then you're getting x1 plus 2/3 equals 1, which means x1 is also 1/3. And so our solutions here, we have a unique solution to this system of 1/3, 1/3, 1/3. Okay, and so here's how we solve a system using an LU factorization of a matrix. So hopefully this was a good review on solving a system via LU factorization, but also how to actually find the LU factorization, right? Okay, and the last problem I want to do for this review, so there are 6 problems in total on this exam. The last 2 are more kind of theoretical, like true, false, and I really want you to ponder those on your own. Of course, you can send me an email asking me, is this right, is this wrong? But for the sake of studying, I think maybe I would rather let you think about those and see if you can find in the textbook whether you think those are right or wrong. What I'm doing here is specifically like methods that we've done in class, methods that are going to show up on the exam, things like this. Okay. Now, what we're going to do in the last one here is a few things. So the first one is says, here's the matrix M representing a system of equations. It's given by 1, 1, 1, 3, 4, 3, 3, 3, 4, and then 12, negative 10, 16. This is going to be an augmented matrix of A and B representing some system, right? Well, first, let's write out, the first thing it asks us to do is write out the system that this corresponds to. Well, this would correspond to the system x1 plus 3x2 plus 3x3 equals 12. X1 plus 4x2 plus 3x3 equals negative 10. And then x1 plus 3x2 plus 4x3 equals 16, right? And so here A would be the matrix 1, 1, 1, 3, 4, 3, 3, 3, 4. And then X would, of course, be x1, x2, x3. And then B would be the vector 12, negative 10, 16 for AX equals B, right? This is exactly, I've kind of described this system as an augmented matrix, written explicitly in terms of equations and as matrices here. Okay, the next part of it asks us to find the rank of A. So we want to find the rank of the matrix 1, 3, 3, 1, 4, 3, 1, 3, 4. Now, to find the rank, remember, this is the number of pivots or the number of non-zero rows in the reduced row echelon form. So let's take this to reduced row echelon form. Well, I can take row 2 to be row 2 minus row 1, and then I can take row 3 to be row 3 minus row 1, right? Why do I do that? Because I want the entries below the A11 spot, I want those to all turn into zeros. And these row operations will get me that. So the first row is unchanged, 1, 3, 3. And then row 2, we're going to have 1 minus 1 is 0. 4 minus 3 is 1. 3 minus 3 is 0. And then we're going to have 1 minus 1 is 0. 3 minus 3 is 0. 4 minus 3 is 1. To get this into reduced row echelon form, next I need to get rid of the 3's above the pivot positions, right? And so the first, I can get rid of the leftmost 3 by saying row 1 is equal to row 1 minus 3 row 3. That gives me 1, 0, 3, 0, 1, 0, 0, 0, 1. And then lastly, I can get rid of the second 3 by saying row 1 is, oh, sorry, how about row 2? There. And this one is going to be row 1 minus 3, row 3, which gives me 1, 0, 0, 0, 1, 0, 0, 0, 1. And notice that the reduced row echelon form of this matrix is the identity matrix, right? The 3 by 3 identity matrix. This means the rank of A is 3, because that's the number of pivot positions. It's also the number of non-zero rows in the reduced row echelon form, right? Now, the next question asks, does the inverse exist? How do we know? Well, there are two ways that I'll mention here that we can use or that will kind of have a light go off that says, yes, the inverse exists. One of them is that the identity matrix is the reduced row echelon form. And so, yes, since the reduced row echelon form of the matrix A was the identity, right? Why is this the case? Because remember, when you're trying to find the inverse, what do? Well, you set up A and the identity, and then to reduce row echelon form, you pass the identity to the left, and then whatever's on the right is your inverse. Well, you can only find the inverse if your reduced row echelon form is the identity here, right? And so I see that it is, in this case, we've seen that it is, which means that the inverse does exist. Another way to determine it is if the determinant of A is not 0, right? And let's look in this case. Let's calculate the determinant. This is just for practice. We want the determinant of 1, 1, 1, 3, 4, 3, 3, 3, 4, right? Here, the determinant, what do, right? We pick the first, the A11 spot, we block out the row and column that those belong to, and then we take the corresponding 2 by 2. So we're going to have 1 times 4 times 4 minus 3 times 3, and then we alternate signs, so minus, and then we go to the next row, the next entry in the first row. So then we're going to have a 3 times, and then we block out the row and column that the 3 belongs to, and that's going to be 1 times 4 minus 3 times 1, and then plus we do the same thing, block out the last 3 there, and then it looks like we're going to have 1. Well, there's a 3, and then 1 times 3 minus 4 times 1. If you simplify all this, you get just 1, which means the inverse exists, okay? So there are multiple ways to determine if the inverse exists or not. In this example, since we already showed that the reduced row echelon form of this matrix is the identity, that would have been enough, right? But just for the sake of practice, I wanted to do that showing by way of the determinant as well. And the problem says, does A inverse exist? We know it does. Now let's find it. How do we find A inverse? Well, we set up AI3, which is our matrix 1, 1, 1, 3, 4, 3, 3, 3, 4, 0, oh, sorry, 1, 0, 0, 0, 1, 0, 0, 0, 1. Now we can do the same steps, right? We've already put this in reduced row echelon form. And so the first step we did was row 2 is row 2 minus row 1, and row 3 is row 3 minus row 1. But now we just need to perform these operations on the right-hand side as well. And we know on the left, we got 1, well, let's just do it. Row 2, 1 minus 1. Well, hang on. First row stays unchanged. The second row, we have 1 minus 1 is 0, 4 minus 3 is 1, 3 minus 3 is 0. 0 minus 1 is negative 1, 1 minus 0 is 1, 0 minus 0 is 0. Then for the third row, 1 minus 1 is 0, 3 minus 3 is 0, 4 minus 3 is 1, 0 minus 1 is negative 1, 0 minus 0 is 0, 1 minus 0 is 1. Right? Let's do the next step, because now we need to, it's in it's in row echelon form. We need to put it in reduced row echelon form. So that means we need to get rid of these 3's. The first one would be to say row 1 is row 1 minus 3 row 2. If we do that, we're going to get 1, 0, 3, and then we'll have 1 plus 3, so 4, right? And then we're going to have 0 minus 3, and then we're going to have 0 minus 0. And then we did nothing to the other rows. Okay, then what did we do next? Next, we're going to take row 1 and replace it with row 1 minus 3 row 3. If we do that, we get 1, 0, 0. And then we're going to have 4 plus 3 is 7. Let's see. Negative 3 plus, where am I? Sorry, this should be row 3, right? And so we're going to have negative 3 plus 0, which is negative 3. And then we're going to have, for the last one, we're going to have 0 minus negative 3, so negative 3. There we go. And then 0, 1, 0, negative 1, 1, 0, and then 0, 0, 1, negative 1, 0, 1, which this means A inverse is 7, negative 3, negative 3, negative 1, 1, 0, negative 1, 0, 1. Okay, now how does this help? Here's the inverse, right? It's good that we're able to calculate the inverse of a matrix. Now, how does this help solve the system, right? Well, when you have AX equals B and if the matrix A has an inverse, well, then you can multiply both sides on the left by A inverse. And then we know that A inverse A is the identity. And so this is just X equals A inverse B. And now we can find X by taking the product, A inverse B, which is 7, -3, -3, -1, 1, 0, -1, 0, 1, and then times B, which was 12, -10, 16 here. If you'll come all the way back to the system that we looked at, right? B was 12, -10, 16, and that came from the system of equations that we were looking at in the first place. And so now to solve this system, all you have to do is take this product, right? And so if you take this product, what you get is like 7 times 12 plus 30 minus 48. And then looks like you'll get for the second entry, looks like I'm going to get -12 minus 10, so -22. And then for the third entry, I'm going to get -12 plus 16, so 4, which looks like I'm going to get X is equal to 66, -22, and 4. And this would be the solution to the system. Okay. So these are the problems, all of like the worked out problems from this exam. I hope this served as a good midterm review and some reviews of concepts and processes and things like this. If you have any questions while you're studying before the exam, please send me an email and I'll be happy to help you as much as I can. But for now, I think just keep studying. Good luck. And we'll see you in the exam tomorrow.